Good evening, everyone, and welcome to our talk this evening. Here at the Scientific Society, we don't quite get talks about space and stuff frequently enough. So today I'm very happy to welcome Professor Alex Halliday, Chair of the MPLS Division here in Oxford, Professor of Geochemistry, and also the Vice President of the Royal Society. And today, Professor Halliday will be talking to us about the origin of the moon. So without further ado, Professor Halliday.
So, thank you very much. Is it possible to get the lights down? So thank you very much for inviting me along. I've got a lousy cold, just to warn you, and so that's why I've got a hot drink here. And if the hot drink starts to go down too much, and I start to sneeze, somebody will rush out and get me another hot drink. So, is this not?
Oh yeah.
Oh yeah. Is that better?
Yeah.
Yeah. So this is one of my favourite pictures. It shows an eclipse of the sun, of course, and but actually it shows the link that we have actually between the origin of the solar system and our own planet, and actually some of the sustainability of life on our planet, and the existence of the moon. Very exciting issue right now. Today what I want to do is talk about some of the controversy about the origin of the moon, and I'm just going to leave you with the present situation is that we don't know, we don't have a satisfactory explanation for how the moon formed. So after many over a century of debate and discussion about it, we're puzzled about some of its features. So I want to bring those things to your attention. So, and one of the problems we've got that I want to talk about is to do with the isotopic composition. I'll explain that to you in a bit more detail in a minute. And that is that the Earth and the Moon are very similar in their isotopic composition. And this is something that doesn't fit with any of the current explanations. And so, of course, Shakespeare wrote this in Othello about how the Moon is actually more near to the Earth. And in some ways, the problem we've got is that the Moon is close to the Earth in terms of isotopes in particular, more than anything else. There are three things that even before we went to the Moon, we knew very well about the properties of the Moon, which made it clear we had to have some kind of an explanation that was consistent with these things. The first is that it's the largest moon in the solar system relative to the size of its host planet, which suggests it might be somewhat different from other objects. Second is it's got a slightly lower density than the Earth, so it has a disproportionately smaller iron core. That's the only obvious explanation for that. And the third thing is that the Moon orbits the Earth around its spin axis. Most of the angular momentum of the Earth-Moon system is in the Moon, the motion of the Moon. Now, when we actually landed on the Moon and brought samples back, we were able to figure out some other things. We could see that there were these sort of two areas if you go to the Moon at night. You can see there's a light area. Most of the Moon is sort of whitish, reflects white against the sun. And then there are these dark bits, which we call the maria. And in detail, we now know with the acquisition of samples that the dark bits are relatively young. They're only about 3 billion years old, whereas the that's very good. Yeah. Whereas the highland bits, the bits that stick up, the light bits, they're quite a bit older. They're about 4.5 billion years old. That's probably the issue. The Moon is actually almost as old as the solar system, and I'll talk about that in a minute. And one of the most important rocks was this white one that you can see here that was returned, sometimes called the Genesis rock. It's one of the best behaved systems in terms of a rock that's been well preserved from the surface of the Moon, and it gives amongst the oldest ages. And that, the exact age of that rock has been subject of recent Nature papers as well, which have changed the impression of when it formed. Now, there are some striking differences between the Earth and the Moon. The first is that the Moon is pretty much dead, whereas at... is that your So one possibility is that the moon is, one striking thing is the moon is pretty much dead geologically, whereas you can be, an undergraduate student on your way to school and discover that actually you've got a volcano going off in your backyard in the UK and elsewhere. So it's pretty clear that actually the planet that we live on is very dynamic and alive geologically. This is a bit of that actually. The other striking thing is that the planet is very alive over long time scales. In the case of the Earth, this is the Baja California, the Gulf of California, from the space shuttle. Rather lovely view. You can see the Gulf of California here. And we know that the Gulf of California is being formed from a sort of ridge coming up here, and actually this whole part of California is being ripped off. And this shows you what the Earth will look like in 50 million years' time. And Baja California by then will have moved all the way up to Alaska, which is quite problematic if you're the governor of California. And so there's a major issue there to sort out quickly before it affects the price of real estate. So the moon is nothing like that. It's clearly a completely dead planet. It's an object that formed some time ago, and really nothing much has happened there very much in the last few billion years. Now, to try and understand how the moon formed, we first of all need to understand how planets form in the solar system. So I want to quickly run through some of the evidence about that right now. And in particular, I want to start off with some observations which are really important, which confirm the long-held view that the planets form from circumstellar disks. This is the Orion Nebula, which you're probably all quite familiar with. This Orion Nebula is just here down in Orion's belt. And if you look in there, you find that there's this cluster of very bright stars just down here forming. If you zoom in on these, you can see this little group of 4 stars here. And as you get closer to those 4 stars, this is a molecular cloud of gas and dust. You can see that there are these funny other objects in there which are sort of dim. If you get really close to those 4 stars, you can see these objects actually aren't quite like stars. They sort of look like they're shrouded in dust. And if you zoom in on some of those individual features, you see that these are actually new stars just forming. They're less than 1 million years old. And they've got circumstellar disks around them of dust, and that's why they don't look very clear. Edge on, they look like this, and side on, they look something like this. And this has been phenomenal confirmation of the ideas of Carrington and Laplace from many years ago that the planets of our own solar system formed from such a swirling mass of dust and debris very early on. Now, if you look at the time scales for the existence of those disks, this shows you a fairly recent paper which basically looked at the number of stars with disks as a function of how old the stars are. And it shows you that basically, if a star is very young, it's very, very common to see them with disks. And as they get off to about beyond about 5 million years, then it's actually very rare to see them having any disks at all. So that suggests that disks basically are disappearing over that time period, and which means they must be going into something, and the most likely thing is that that dust is being accumulated into planets, and it gives you a rough idea from space of how quickly we form planets. That is probably over a few million years. Now that dusty disk we have samples of for our own solar system, and we get those samples in the form of meteorites, and they're a phenomenal archive of information. We get about 50 million kilograms of 50,000 tons of material landing on the Earth every year. Most of it's in the form of very, very fine dust, but occasionally you get quite big chunky meteorites landing. This is one very famous one called Murchison, which fell in Australia a few decades ago. It became famous because they found organic molecules in it. It's got lots of organic material, and people started to think, make a connection, potential connection between this meteorite and the origin of life. Fred Hoyle in particular drew that connection, suggested maybe life came from other parts of the solar system. Now if you take one of these meteorites apart, these are very primitive kind of meteorites that actually haven't made it into planets yet, and they're called chondrites. And if they've got carbon in them and lots of material, these organic molecules, then we call them carbonaceous chondrites. And if you take a look inside these, you find that there are a number of interesting objects in there. So these sort of funny, irregular white things are things turn out to have a chemistry that's extremely refractory, as if they condense from a hot gas of solar composition at very high temperatures, over 1,000 degrees. And they're thought to be, they're called calcium aluminum refractory inclusions, and we find that they are the oldest objects that formed in our solar system. There are older objects that came in, which I'll talk about in a minute, but actually they are the earliest objects we've been able to find that actually formed in the solar system. And then you've got these other objects that make up most of the meteorite, which are these round things, which are called chondrules. And that's why these things are called chondrites. And a lot of these meteorites have lots of these chondrules. Nobody knows quite how they're formed. There's about 7 or 8 different theories. But they formed 1 million or 2 years after the start of the solar system, after these other objects, after these calcium aluminum refractory inclusions. They think they might have been produced by some kind of flash melting in the disk at a very early stage. And there are theories about why that might be. Now, there's another kind of object you find in which is pre-solar. And this is, I'm not going to have time to talk about this, but this is just fantastically exciting stuff, which was discovered about 20 years ago. People realized that if you dissolved up that meteorite with strong acid, like hydrofluoric acid and all that stuff, you were left with some grains that didn't dissolve very easily, which are made of things like silicon carbide and graphite, things that typically don't form in most rocks, the Earth's surface. And these things have very strange isotopic compositions. They're completely different from anything on the Earth. And people realized actually they are grains of material condensed in the envelopes of other stars. In other words, across there in the Natural History Museum, you've actually got rocks rather like this, and if you dissolve up those rocks, you'll be left with some grains that formed around other stars. And I find that one of the most mind-boggling, exciting things, because it's actually, you've actually got an archive of what's happening in other parts of the galaxy in your meteorite collections. So these things have been incredibly important for looking at the isotopic compositions to use them to figure out how stars actually work, because of the nucleosynthetic pathways they tell us about. Okay, so the net result of those grains with very weird isotopic compositions is that it means that depending on the mixture of them, you can get different kinds of isotopic compositions in meteorites. So this is an element, zirconium, that's got a range of isotopes with different proportions of neutrons, different numbers of neutrons. And some of these are produced by what we call the S process, that is, they're produced by slow burning in irradiation of neutrons. And some of these are R process, and in particular this one, zirconium-96, because you've got to get from zirconium-94 to 96, you need to have a very high flux of neutrons to get over there, because zirconium-95 decays so fast. So it tells you you've got an R process nuclide, which means rapid process, which is probably requires something like a supernova environment. And the existence of these nuclides can tell you about the kinds of stars and the kinds of stellar processes that might have been around. But when you actually get these into dusty disks, there's a certain amount of heterogeneity, and they end up in chondrites, like we saw, or these rubble piles, and there could be variations within the disk of material with different isotopic compositions, depending on exactly how they're all mixed together. And this turns out to be quite an important way of fingerprinting the material in the circumstellar disk or in the planets that we have today. We use techniques rather like this and to identify that meteorites have come from Mars, for example. You can tell which ones come from Mars because they've all got the same proportion of isotopes. Not just nucleosynthetic, but other forms of variation as well that can be produced. So I'm going to talk about a lot of these kinds of variations and the fact that the Earth and the Moon actually don't show any difference because it's an important constraint. Now there's another kind of variation that's really important for understanding the origin of the Moon, and that is variation produced by radioactive decay. And this basically shows you a schematic plot very schematic, of synthesis in stars. So you can imagine a galaxy with lots of stars, and gradually over time, a stable isotope like oxygen-16 gets gradually built up with more and more of the stuff. If you assume you're producing it at some kind of steady state rate, then some of those atoms get trapped in the planet or the sun or the planet that you're in, and then that proportion doesn't change very much since then. But if you've got a radioactive isotope, then it's slightly different. If it's a long-lived one with a half-life of billions of years, like uranium-238, then as you produce it, then it's also decaying at the same time, and then when you stop producing it, it just decays. And we use this for measuring geological timescales, like dating rocks, and also figuring out when the solar system first formed. I'll talk about that in a minute. And you can see there's a certain amount of change that takes place over this period. Of course, this is all schematic. This is a very short time compared to the overall time since the solar system formed. And there are a whole variety of those kinds of, whole variety of those kinds of nuclides that we can use with half-lives of billions of years, and that we've been using for isotope geochemistry for many years. And so the lab across the road down the road in Earth Sciences has got one of the most sophisticated labs. It's one of the most sophisticated labs in the world for doing these kinds of measurements and other kinds of measurements. The kinds of things that traditionally people have worked on are these long-lived nuclide systems, which have been very effective for actually dating rocks and geological timescales. Now, as well as that, you can also have short-lived nuclides, which have got half-lives such that they're actually pretty much extinct today. So uranium-238, there's about half as much uranium-238 today as there was at the start of the solar system 4.5 billion years ago. But if you've got something with a much shorter half-life, then while it's being created, it's already decaying. It'll eventually form a sort of steady-state production rate here, steady-state value here. And then once you stop producing it, like you cut off the source of the nuclide, because it's no longer, you cut it off from the stars where it's being produced, then it will actually decay very, very rapidly. And the nice thing about this is you can see that the change in abundance is very, very quick over the time interval that you're looking at. And the great thing about that is those nuclides all produce daughter, and so there's a big change in the daughter that happens only in a very restricted time window. And if you can measure that isotopic difference, you can use it to very powerfully constrain exactly when that particular reservoir or rock or mineral or whatever it is actually formed. So these are the short-lived nuclides that have now been discovered in the early solar system. The first one was discovered in about 1960, which was iodine-129, which decays to xenon-129. And it was discovered by discovering excesses of xenon-129 in the xenon, in a meteorite. And they were correlated with the amount of iodine that was left. This is iodine-129. It's all decayed away because the half-life was only 16 million years. But there's iodine-127 still around, and so you can compare the iodine-27 amount with the xenon-29 and show that the parent element was correlated with the excess of this daughter isotope. And you can use that to figure out timescales. All of these have now been discovered, I think, except for cesium, barium. There's still a bit of question as to whether that's been found or not. People are not sure about that. Now, some of these have been incredibly useful for figuring out timescales in the early solar system. Aluminium-26, which decays to magnesium-26 with a half-life of 700,000 years. And hafnium-182, which decays to tungsten-182, which is the one I've mainly worked on, with a half-life of 9 million years. Those have been really, really powerful for figuring out how quickly the planets and the Earth and Moon first formed. So let's take a look at hafnium and tungsten. These are the isotopes of hafnium which you have around today. And these are the isotopes of tungsten. There's a small one there, tungsten-180, which is so low in abundance you can't see it very easily. But at the start of the solar system, there was also hafnium-182. And this shows it magnified by a factor of 1,000. There wasn't very much of it. But there was a small amount of it, and with a half-life of 9 million years, it gradually decayed, or rather quickly decayed, over periods of 50 to 100 million years, to produce small variations in tungsten-182, and you can, using precise mass spectrometry, if you come up with techniques for ionizing tungsten in the laboratory, measure that small isotopic difference, you can figure out how much time has elapsed from the small change in the abundance of tungsten 182. So to do all this work, we have to build sophisticated clean labs, separating these elements, which are very often present in trace amounts. And we then have to separate these elements from rocks, dissolving them up with acids at very low blank, and then separating them using ion exchange chromatography, using ion exchange columns. And then from there, we basically put them into very sophisticated mass spectrometers. This is one of the larger mass spectrometers in the world, the new 1700, and you can see Rhodes House there in the background. This is over in Earth Sciences. So this particular machine is used, it's a plasma source mass spectrometer. It's been very successful at being able to do measurements of tungsten in particular, which we couldn't do before about 1995 when we actually got the first one of these instruments in America. Of course it was built in Britain. The first one went to America, the second one went to France, the third one to Switzerland, the fourth one went to Japan, and eventually the British got one. Okay, so if we use those techniques, we can start to put together a time scale for how the solar system formed, our own solar system. And what you find is that these earliest objects I talked about, the calcium aluminum refractory inclusions, they formed at this date here. This really is the precision which we can get down to less than 1 million years, 4.5 billion years ago at the start of the solar system. So these are very precisely dated now. And these things, even though we're not quite sure how they formed, they are the oldest objects with isotopic compositions that suggest they did form in the solar system. Now you can use tungsten isotopes to look at metal in particular, and these big things that you see in your museums, in particular iron meteorites, big chunky things, which survive rather well weathering on the Earth's surface, and so they're fairly obviously meteorites. And you look at these and you can find that they are extremely old, very early. And some of those have tungsten model ages which suggest they formed in about 1 million or 2 million years at the start of the solar system. These represent metals segregated by core formation from something of an asteroidal size, something between 20 and maybe 400 kilometers in size, heated up, melted, actually segregated metal, dense metal, metallic liquid, and formed a core. So it tells you that planetary processes and formation of cores was going on in the first 1 or 2 million years of our own solar system. We've got Martian meteorites as well. There's many of these now. I think there's about 50 of these now that have been found. And these basically have similar very early ages. There are ways of showing that Mars must have accreted and formed fantastically fast within a few million years, within a couple of million years anyway. So it actually represents a very, very rapidly growing sort of planetary embryo. It's not very big, it's only about 10% of the mass of the Earth, but it formed pretty fast. Then we have those funny things that we call chondrules, these round things. We don't know how they formed in these things we call chondrites. And they suggest they appear to have formed around the same time, about a couple of million years after the start of the solar system. We've got an indirect way of using these short-lived nuclides as well, and that is, if you look at one of the moons of Jupiter, there is evidence from the degree of melting that's taken place in the planet that this has to have formed early when there was live iron-26 around. That's the argument. That would have generated enough heat to cause the melting. And this basically gives a model age for this moon of Jupiter of a few million years, and that suggests that, Saturn. That suggests that Saturn formed in a few million years. So this all looks very consistent with what we can see from circumstellar disks, that you're forming planets within a few million years, taking all that dust and debris and turning them into planetary-sized objects. So then you've got the moon, and this is that photograph I showed you, this 60025 lunar north-side from the lunar highlands. And if you actually analyze the isotopes in the moon and try and figure out how old it is, you get a much younger age. There's both evidence from hafnium tungsten that it has to be at least 30 million years old. You run out of leverage after about that period of time because of the half-life of hafnium-182. But you can also use these longer-lived nuclides like rubidium strontium, and that gives you an age of roughly 100 million years of formation of the moon. So there's something funny here. You've got an object about 10%, about 1% of the mass of the Earth. So kind of sort of asteroidal size or small moon size, a standard moon-sized object. And all the theoretical models for when those things formed from dusty material suggest they form in the disk quite rapidly by gravitational attraction. After you get up to about 1 kilometer in size, gravity takes over, and you use up all the material nearby, and you form objects of moon size, typically in about 1 million years or even less than that. And here we have a moon-sized object that clearly formed much, much later than that. It has an age which suggests that it formed probably about 100 million years. It might have been 150. There's a bit of uncertainty around these numbers, and they're based on models which you have to make some assumption for that. So any model for the origin of the moon has to explain how it formed really, really late. And so let's go through some of the models that have been around, some of the historic models. And this is the son of Charles Darwin, George Darwin, who proposed this model in 1878, fission. And that is the idea that the Earth started off as a molten ball that was spinning incredibly rapidly. And in the process, some of the material, it became unstable, and some of the material spun off from the moon and formed a satellite that went around it. A number of people have proposed this cannot possibly be correct because the tidal effects would have been so huge of this material that the moon wouldn't have formed. It would have been basically fragmented as it started to move away from the surface of the Earth. And so you would never actually get it to form a moon that way. And other people have argued about the fact that it would actually require the Earth spinning fantastically fast as well. People have also argued about the manner in which you would actually be able to stop the moon from just carrying off out into space. So fission hasn't been very popular. Another model that was proposed was by this guy, Thomas Jefferson Jackson C., who was an astronomer, observer, and he basically came up with this view that the moon probably formed simply by co-accretion. He spent a lot of time working on Saturn's rings and things like that, and basically decided the best way of forming the moon was this way. This was, his ideas were somewhat thrown out, principally because of the fact that they found that some of his observations had been fabricated. So he kind of lost a bit of credibility, and the theory kind of lost credibility to some extent with that. But one of the problems with the co-accretion model is that it doesn't really explain why the moon is sort of spinning around the Earth. It doesn't explain why the moon has got a lower density than the Earth. It also doesn't explain why the moon formed late. So it's not a very attractive theory from what we know about the moon. Then Harold Urey, who won the Nobel Prize for the discovery of deuterium, came up with the idea of capture. Urey did a huge range of things. He was an astonishing scientist. And as you know, he got involved in the 1950s with the origin of life as well. But his idea was that the moon is most readily explained as a wandering planetesimal that was caught into orbit around the Earth. The main problem with this theory is it doesn't really explain why the moon is actually moving away from the Earth at the moment. It also, one of the striking things about it is it doesn't really explain why the moon is late. There's no obvious explanation for that. So capture has been pretty much discounted. Now in 1984, there was a very famous meeting in Hawaii called to discuss the origin of the moon. And the reason was that nobody could really make any sense of these three competing theories. None of them seemed to work. There seemed to be basic things that didn't work, and particularly the new data that had come back from the Apollo missions on lunar samples, which were incredibly important because actually, I don't know if you know, but the Apollo missions originally were not supposed to collect any rocks at all. The basic idea was you had to send some people up there and then bring them back, and that was it. And there were strict instructions not to bring anything back. So it took a team of scientists in America to really go and persuade government, but actually this was a phenomenal opportunity for science. When there's a celebration of the Apollo landings a few years ago, and they were talking about Armstrong and what he accomplished, there was a piece in the newspaper, I think it was the Times, about what had been accomplished by the Apollo landings. And everyone talked about it, including the Astronomer Royal, actually, talked about it as a great technical achievement and a fantastic political achievement, but actually it wasn't important scientifically. And actually that is so unbelievably wrong. If we didn't have those lunar samples, we wouldn't be able to figure out all this stuff about the origin of the moon. And we'd have a completely wrong idea about how the moon formed. So those lunar samples create a whole lot of exciting science around the world. And this meeting in 1984 was trying to bring all those strands of evidence together and discuss them. And the idea that people came up with was rather similar to a model that had come up in 1979, which was that there had been some object that had hit the Earth, and maybe several objects that had hit the Earth and produced debris that had gone into orbit around the Earth. And that material, that debris, had basically coalesced to form the moon. That idea, by Hartman and Davis back in the 70s, didn't explain the angular momentum feature. And so in 1984, the Origin of the Moon meeting, it was proposed that actually you didn't just have lots of little impacts, you had one giant impact. And that actually generated enough angular momentum in the Earth-Moon system to have the Moon going around the Earth. It turns out that back in 1946, a very similar idea had been proposed by Reginald Daly, who was a very famous geologist, who already proposed that actually the Moon came out as an impact origin. It wasn't particularly detailed in terms of his ideas, but he was already of the opinion that the Moon basically formed from an impact. But people have only just rediscovered this paper fairly recently. So the Moon forming giant impact since 1984 has been the main theory for the origin of the Moon. And it's basically traditionally been viewed as an impact between the Earth, when it was about 90% formed, and another planet that collided with it and made up the final 10%. And the debris from that giant impact, the 1% that was sort of knocked around outside, coalesced to form the Moon. That planet that collided with the Earth is sometimes called Theia. So Theia basically was, I asked one of my team in Zurich to come up with find out who the mother of Selene was, who was the goddess of the Moon, and he told me it was Theia, we should use her. So basically the mother of Selene, the goddess of the Moon, is Theia, and she's, those of you who know the muses. So we called the planet Theia. So there have been a lot of simulations of this process, of this giant impact, and this is one of them that came out a while ago. It's a 3D simulation, it's quite nice. It shows you the enormous energy. The blue in this is, these colors are going to be contoured for temperature. So the blue is 2,000 degrees, and red is 9,000. Oh, sorry. There you go. So this shows you the Moon, Theia rather, coming in with a glancing blow, hitting the Earth on the side. I like the 3D simulation because you actually see around the object as it's growing. The temperature of the planet immediately goes up to incredibly high temperatures. Most of the temperature rise is actually in the earliest material from the impacting planet hitting that surface, as you might predict. It generates this angular momentum, generates a debris disk around it, and this thing goes on for a little while, and from that you can eventually form the Moon. These simulations are called smooth particle hydrodynamic simulations. They use a lot of computer code, but the actual size of the objects that are being, you divide the planet up into lots of little objects, and each one's about the size of Paris. You know, they're quite large objects, so it's not very good for looking at the details of fluid dynamics, but it's the best we can actually get to very easily at the moment. Now, if you track these simulations in more detail, actually track the material and where it all comes from that ends up in the moon, then you get a very interesting observation. This shows you one of these simulations from a more recent simulation. It divides the two planets into silicate portion and metal core, and it color codes them so that you can actually see the difference between the two planets. So you see one object is green and the other object is yellow. Now I've got a hang on. Okay, so here's the two objects. Here's Theia in yellow colliding with the Earth when it's 90% formed, and there are the two cores there. And I just want you to see what happens in terms of green and yellow as this thing goes on. So this is real time, how long it would have taken. And what you end up seeing is that actually the main material that makes up that disk that goes around the Earth, from which the moon forms, is the impacting planet Theia, the yellow. And this is maybe not too surprising. The planet is coming in from the side. There's all that gravitational pull on the Earth, so you expect itself to stay more strongly coalesced. You can see the two bits of core material merge with each other very effectively because there's a lot of density in that metal. But basically the disk ends up largely being dominated by yellow bits rather than green bits. In other words, it's Theia that basically dominates the material that makes up the moon. Now, this is where we encounter the problem. So I talked to you earlier about stellar nucleosynthesis and the fact that we have isotopic variability in the solar system. Oxygen is the most variable element isotopically in the solar system. And we realized this in the early 70s when people started analyzing meteorites for their oxygen isotopic composition. And this actually was originally thought to be due to stellar nucleosynthetic variation. Now we think it's due to something else in the early disk, due to the radiation. We don't have to worry about the details of that. But it provides a very, very powerful fingerprint for material in the circumstellar disk. So this shows you the oxygen 17-16 ratio expressed as a per mil deviation from 0, which is roughly where standard mean ocean water is, average water. This is oxygen 18-16 ratio in per mil deviation. And everything that, because this is a 1 atomic mass unit difference, and this is a 2 atomic mass unit difference, 18-16 and 17-16, this slope along which mass-dependent fractionation lies, so everything changes in isotopic composition when you evaporate and things like that, along a mass-dependent line, it'll lie along this terrestrial fractionation line, which is shown here, which is a slope of 0.5. If you look at meteorites, the numbers go all over the place. You can find that there's all kinds of variability. These are carbonaceous chondrites, different kinds of carbonaceous chondrites, and the numbers are highly variable. Now, if you zoom in on this area here where the Earth lies, this is the terrestrial fractionation line again. These are meteorites from Mars. These are meteorites from an asteroid called Vesta. They all lie on mass-dependent fractionation lines with a slope of 0.5. That number is real, it's not a mistake. And so why it's different isn't particularly clear at the moment, but it may be a different parent body, we don't know. And this shows the terrestrial fractionation line, and these are the data for the moon. So these are super high precision data, very long high precision mass spectrometry runs, and they show that the oxygen isotopic composition of the moon is absolutely identical to that of the Earth. It's as if the atoms in the moon came out of the Earth. But everything else in the solar system is different. We've analyzed in meteorites. And so the question is, if those simulations are correct, and the moon formed from this other planet, how come the oxygen isotopic composition of the Earth and the moon look so similar? In fact, these have been run to such high precision that we can't resolve the difference down a few ppm. This paper came out, I think it was last year, they've gone to even higher precision than we were able to go 10 years ago, and they claim to be able to resolve a small difference. But that small difference is mainly down to the things have been added to the Earth since the moon formed. If you correct for that, basically they're still the same. So people have tried to explain why this might be. And one suggestion that we came up with back in 2001 was that actually Theia must have formed at the same distance from the sun as the Earth did. So these planets had the same mixture of stuff and they looked identical. But the problem with that theory is that it doesn't explain why the moon took 90 million years to form. The stuff's at the same heliocentric distance, you've got these two planets going around, why didn't they collide earlier? It's quite hard to see why that should be the case. People did a lot of simulations of the chances of this happening, and they said it's pretty unlikely. And this very nice paper came out from Caltech in 2007 by Parlave and Stevenson, proposing a new model. And that actually, after the two planets collided, the temperatures were so high that actually you had a magma ocean on the Earth, but you also had basically a silicate vapor, a rock vapor atmosphere, and the disk from which the moon formed actually would have been a hot vapor disk from which the moon condensed. You would have had droplets condensing and then gradually the formation of the moon. So the idea was that basically if things were hot enough for long enough, you could have actually had mass transfer between the Earth and this disk by diffusion and by convection and mixing. And that would have been long enough to actually allow volatile elements in particular, like oxygen, a large part of those, the elements, a large part of the oxygen would have been able to mix and equilibrate. So you'd end up with the same number of two objects, even though the planet came from somewhere else. So subsequently to that, a group in Chicago produced a really nice piece of work, very high precision. Sorry, you can hardly read this, I suppose. But this is for titanium, which is a highly refractory element, which wouldn't work without vapor augmented, condensed, and formed solids very early on. This shows you, don't worry about the details, these are the chondrites, they're highly different. You can see all the objects are different, and here's the Earth and the Moon here. There's a bit of correction you've got to make for cosmic ray exposure. Once you make that correction, the Earth and the Moon are basically identical. So this doesn't hold just for more volatile elements like oxygen, it holds for highly refractory elements as well. So then you could argue, well, maybe Halliday was right and actually things did actually form at the same heliocentric distance. But there's further evidence that actually it wasn't just material from the same heliocentric distance, it was atoms that came out of the Earth that actually went into the Moon. So I'll take you through that bit. And to do that, I've got to give you a little detour and explain something about the Earth that makes it very distinctive, which allows us to fingerprint atoms actually coming out of the Earth itself. And that's to do with the size of the Earth. The Earth is sufficiently large that it's got a high pressure iron core. And it was shown back in the 50s by this Chicago geophysicist, Francis Birch, that the density of the Earth's core was wasn't quite right for solid iron, solid or liquid iron. You had to have something else in there that was of lower density. And he proposed that there had to be a 10% of a light element, roughly 10% of a light element in the outer liquid core. It doesn't have to be exactly 10%, it depends on which element it is, of course. So people since then, including people in Oxford, have been working on trying to figure out what that element might be. And the obvious candidates are hydrogen, carbon, nitrogen, oxygen, sulfur, and possibly silicon. Okay, so under reducing conditions in high pressure and high temperatures, silicon will go into metal, and people started proposing this. And there's actually quite good evidence that might be the case. If you take those rubble piles of carbonaceous chondrites, which represent average solar system material, take out the metal, take out the volatiles, this is what the planet should look like. The Earth, the rocky Earth, planets like Earth should look like. And this is actually what the primitive mantle of the Earth, the mantle and the crust, do look like. And you see there's a deficiency in silica in the silicate portion of the Earth. We don't have quite as much silicon as you would expect, and judging by what we have in the average solar system, which suggests maybe some of the silicon has been lost to the core. So we published a paper in 2007, actually providing evidence that this indeed was the case, using silicon isotopes. So the basic idea is that this is another mass-dependent thing. So, but it's a mass-dependent fractionation that depends on bonding. So the difference between silicon going into metal and silicon going into silicate is huge in terms of the strength of the bonds. And the net result is that there's a mass-dependent fractionation between silicon in metal, which is relatively light, slightly isotopically light, compared with silicon in silicate. So the effect of this is to change these relative proportions of an element. This is just a fictitious element, don't worry about what it is. And they go like this, basically the lighter, heavier isotopes, you get more of them, and the lighter isotopes, you get less of them, or the other way around. So if you look at silicon isotopes in a variety of meteorites, like the ones we've just been talking about, the chondrites, samples from Mars, samples from Vesta, as a function of silica content, but you don't have to plot it versus silica, you can plot it versus anything. This is data produced at Oxford in the last few years. This is the silicon isotopic composition expressed as per mil deviations, again, rather like we did with oxygen. So this is a 30-28 ratio for silicon. You can see that this is roughly where they will plot. These are the most precise data at that time that have been produced for these kinds of meteorites. These are the data for the silicate Earth. And they're isotopically heavy. So samples from the Earth are isotopically heavy because light silicon has gone into the Earth's core. So there's been a fractionation that's taken place between the silicon in the silicate portion of the Earth and the silicon in the metal portion of the Earth. Now, what happens if you look at the Moon? That's not got a high pressure core. It's got a very small core. But actually, the isotopic compositions are identical to those of the Earth. And there's no obvious explanation for why that should be the case, unless the atoms in the Moon actually came out of the silicate portion of the Earth. There are similar arguments that have been made based on tungsten as well. I won't go into those. But this actually suggests there is actually some way of getting the stuff out of the interior of the Earth into that disk, and that's what you're looking at. So to quote Shakespeare really, what he meant to say was this. It's very early, she comes more in the Earth in isotopic composition than she was one, and makes scientists mad. So William Shakespeare and others have made this very clear that we've got a problem here and a dilemma because the simulations don't fit what the isotopes tell us. So a couple of years ago we had a meeting in the Royal Society to try and thrash out this problem. Myself and a guy called Dave Stevenson at Caltech, the same guy who I showed you the simulations from, basically organised this meeting. We have a meeting seems to be about every 14 years. So we had that one in 1984 in Hawaii. There was another one we held in 1998 in Monterey, California. So then we had one in 2013. And the basic idea is every 15 years you just get so fed up you have to have an argument. So we had 4 days of argument. And it was just fantastic. It was the most argumentative meeting between dynamicists and geophysicists and geochemists like me that I've ever actually experienced. Now, one of the things that actually really precipitated that meeting was some new simulations that came out that tried to get around this problem. So they said, let's assume the isotope geochemists are correct. What are the other possible explanations? Let's assume there's something wrong with the simulations, and is there another way of doing them? There have been a few of these. One is this simulation that came out from the Swiss group of Willy Benz, Royfer et al. They use the same size objects as we talked about just now, but they basically have what's called a hit and run model where you basically hit the Earth very, very quickly head on and lose a lot of debris from the Earth-Moon system. There's no easy way of slowing the objects down. It's called a hit and run. It's the same reason why people think Mercury has a high density. They think the outer portion was struck by another planet, which then went off and probably went to the sun. People have suggested maybe something else happened like this in the Earth-Moon system. This has gained some credibility, but people haven't been wildly excited by it. Then there are other models that are basically based on the idea that the Earth was already spinning very, very fast. So Robin Canup, whose simulations I showed you before, proposed that the Earth and the impactor were actually very similar in size. Don't have to worry about the detail of this, But basically what they do is they assume the Earth is actually already spinning very, very fast. You don't have to worry about the angular momentum. And you hit the Earth head on, actually generate a angular momentum from earlier events, not from the actual giant impact. And then you generate debris that comes from these two objects. And they roughly end up with the debris looking in similar proportions to the final Earth. But this is probably the one that's gained most credibility, and this is the one that actually started off this idea of the Earth spinning very fast. And this is the paper that came from Harvard, Chuck and Stewart. They actually come up with Earth's thaers that can be quite small, in this case 2% of the Earth's final mass, relatively tiny objects. They have the Earth spinning with a day of, in some cases, 2 hours, really, really fast. So they don't try and generate that angular momentum from the collision at all. They have the Earth already spinning very fast, and then they hit the object with a glancing blow. And this shows you one of those simulations. So this is spinning so fast that it looks, of course, it looks oblique on the side because it's spinning extremely fast on its axis. And this looks at it down from above. Here are the two objects colliding. So Theia is in yellow, and the Earth is in green. It's rather like the one I showed you earlier on. But this time, with this head-on collision, most of the debris actually comes out of the Earth and not out of the impacting planet Theia. So this thing rolls on for a while, and then 24 hours you end up with a quite extended atmosphere with debris disk that's dominated by green. In other words, material came from the Earth. And you couldn't resolve that difference with oxygen isotopes or the other techniques. Now, there's a major problem. Let's go back before I show that. There's a major problem with that model, which has caused much argument and debate between Harvard and MIT in particular. So there's a very distinguished individual at MIT who works on the dynamics, celestial dynamics, and he pointed out that the chances of this actually happening may seem quite reasonable, but the chance of getting the circumstances which you have to slow the Earth down from that event are very, very slight. So Chuck and Stewart basically advocated that while you might have the Earth with a day of two hours, you then got to slow it down after that impact event to get to our 24-hour day. And the way they actually suggested doing this is with a resonance, a tidal resonance between the Sun, the Earth, and the Moon. And the chances of this being aligned, things being aligned in this way appear to be quite small. So this basically led to a large amount of argument at the Royal Society meeting. It basically means that even though this model is the latest model, people haven't accepted it yet. And we don't actually have a model that explains both the dynamics in a way that people feel is satisfactory and the isotopic compositions. The dynamics, you feel that there has been a thinking for a long time that actually these collisions are how you build up a planet and make a terrestrial planet like the one we've got. And so there's the general assumption that you have to have some kind of a process that must be a sort of normal kind of planetary process to explain how you build this thing up and end up producing a moon. And actually what we seem to have got ourselves into is a situation where A, the moon appears to fall extremely late, it's rather an oddity, and we've got some rather unusual circumstances that are required to explain both this isotopic composition and the dynamics. And nobody can quite believe that it can be that difficult to form a moon. So there's means that basically the community is completely out right now on how a moon form. There are a couple of other things that haven't been explained by any of these models, and the first is this, that if you look at what we call moderately volatile elements like potassium or rubidium, the alkalis, those are shown here as rubidium relative to refractory elements, don't worry about details of this, rubidium relative to barium, and potassium relative to uranium. you can see that these are the average solar system materials. They plot up here, relatively volatile rich. Mars is fairly volatile rich. Earth is here. The moon is actually right down here. It's extremely depleted in volatiles, moderate volatiles. And none of these models explain that at the moment. They don't know quite why that might be the case. If the atoms did come out of the Earth, how come the moon looks different chemically? We don't have an explanation for that for the moon either. And finally, what's been causing massive vexation and confusion is some new data that's been coming out of these soils. This is Apollo 17, and one of the things the astronauts noted when they came to Apollo 17 was that the ground was kind of orangey. And they got lots of samples of this orange soil, took it back to the laboratory. And what they found was that this orange soil was made up of glass beads. Glass beads that erupted billions of years ago on the surface of the moon by fire fountaining. They are extremely high temperature liquids that have chilled, and they basically suggesting they came from very deep within the moon at relatively high temperatures. And they've got interesting chemistry, but they've also got very interesting water contents. And this paper came out of Nature in 2008. There's been a lot more work done recently, including deuterium-hydrogen ratios, showing that the water contents of these things are actually not very different from the water content of basalts coming from the Earth's interior today. There's a lot of argument about the results, but actually there seems to be, in terms of their interpretation, not the data. But the suggestion is that actually the moon isn't that volatile, depleted deep inside, which is fascinating if that's really true. So there's still tons to sort out about the moon. I'd like to be able to give you some nice, tidy explanation that I could regularly say, oh, now I've figured that out. I'm really glad you told me, but I can't tell you anything in the way of a final explanation. Well, I can give you some conclusions of what we do know. First thing is that we now know that planetary objects up to about Mars size typically were built within a few million years of the start of the solar system. The moon formed much, much later, probably sometime between 70 and 150 million years, depending on which assumptions you make about the model ages. Oxygen, titanium, chromium, silicon, and tungsten isotopes, I didn't talk about all of these. They all provide evidence that pretty much anything you measure, actually, provide evidence that Theia formed close to Earth, or more likely the moon's atoms actually came from or mixed with those of the Earth. This is hard to reconcile with current dynamic models. Currently, there is no satisfactory explanation for how the moon formed. If the moon came from Earth, then volatile elements were lost, but we don't know how, why the Earth is more depleted, why the moon is more depleted in volatiles than the Earth. And surprisingly, there is evidence that the deep moon may be not so different from the deep Earth in terms of its water contents. That's it. Oh, this is just to show you that Snoopy got there first.
Question time.
I don't quite understand what's happening to the molecules that changes. I mean, if the moon formed relatively recently, what has happened to those molecules that's caused the isotopic composition to be different to an object which is coalesced in previous times?
Sorry, I didn't quite understand.
I mean, the whole thing has been premised on the fact that the isotopic ratios tells you when that piece of rock was formed.
Oh, you mean the radioactive ones formed by radioactive decay?
Yes.
Yeah, yeah.
And so what's actually happening to the, I mean, if something coalesces at a certain time, what's happening to the molecules that tells you that isotopic composition a million years ago rather than a billion years ago, it's all come from the same dust, hasn't it, originally?
Yeah. So the timing thing is to do with decay of parents to daughters. So you're using a particular isotope to measure that.
Yes.
And what you're actually looking at in the case of tungsten isotopes which are used for the dating, is simply the variation in one particular isotope that you know can only be produced by that radioactive decay scheme. And so you measure that isotopic abundance, it's different. Everything else is the same except that one isotope, which is different because of radioactive decay. So that tells you that that's to do with radioactive decay and nothing else.
But why is it decayed at a different rate on the Earth and the Moon, say, or the Earth and Mars? Why have they decayed at a different rate?
No, they haven't. They decay at the same rate. So they decay at the same rate,
yes.
but they produce, depending on when they form, it'll produce a different amount because of the decay of the parent relative to the daughter. Because of the decay of the parent, you actually get, and the amount of the parent relative to the daughter, you'll get a different isotopic effect.
I don't get it.
In order to further assess the composition of the moon, how deep would you need to dig beneath the surface to get more precise samples?
So, well, the key thing with the moon is that it's exposed to cosmic rays, and so some of the isotopic composition of the Earth's at the moon's surface have been messed up by that cosmic ray exposure. And you can measure that cosmic ray exposure with certain kinds of elements that have isotopes that are particularly sensitive to those reactions, and you can actually calibrate it quite well. But to get around them all together, you either need to use a sample that hasn't been exposed very long, or you need to dig down deep. So we've talked about that as an idea, but actually to go back to the moon, the ideal thing would be to go down as, a few meters down, actually below where you get the cosmic rays coming in, and then measure its isotopic composition to incredibly high precision relative to the Earth. And that would actually allow you to get around some of these problems of cosmic ray exposure we've seen. We see that in the tungsten isotopes, but we also see it in titanium isotopes. So that would be an incredibly useful experiment to do if we actually managed to do that. To get these, to look at these water contents that we talked about, we don't know quite where that's coming from. That's coming from kilometers down, hundreds of kilometers down inside the moon. So that's a different sort of scale problem altogether to get down to those kind of source regions.
Is there currently a proposal for going back to the moon and recovering such samples?
Yes, we've talked about going back to the moon with robotic missions and bringing some samples back. There are sort of some plans out there, but they keep getting delayed. But ESA's quite interested, and NASA's quite interested in it. But Mars always ends up being the priority, and it's basically because people are driven by the idea of life on Mars.
I don't know if these are just far too improbable events, but is it likely that some of the problems might be solved by having a dual impact rather than a single impact, so that you get a secondary impact when the Earth has been spun up or made more molten, more hot, or had the large kind of like atmosphere around it that would then enable a more Earth-like surface, a surface of the Earth-like moon to be created from that secondary?
Yeah. So that was kind of rather like the idea of Hartman and Davis. And actually the other thing is that as we get to these models where the Earth is spinning very, very fast, and you're actually trying to get stuff out of the Earth with an impact, the models are looking more and more like Darwin's original fission model, which everybody discounted, where you've got the Earth spinning very, very fast. And so where people say you can't hold on to the stuff, So in the case of the latest theories, what you're doing is basically hitting the Earth effectively and producing fission in the process. And people have talked about maybe hitting the Earth more than once as one of the ways of doing that, putting some debris up and then putting some more debris up. I think the original models were all based on the idea that the only way you could explain this angular momentum was with the giant impact. You've got most of the angular momentum of the moon. There must be a relationship there between the formation of the moon and that angular momentum. And it's only recently people have started to think about the fact that actually these things could be completely unrelated to each other.
The just explain that again. It's not possible to have a capture model. What if they're in the same sort of orbit you're talking about? Even that not work?
So the capture model, the reason why people discounted it was once they got samples back from the moon, they could show that even roughly, it's quite clear fairly early on that the oxygen isotopes look broadly similar between lunar samples and terrestrial samples.
So if they formed in the same sort of
so that's right, if it formed at a similar kind of heliocentric distance, that might be one explanation. The other problem with the capture model though is that it doesn't explain why the moon's got lower density, why it's got an iron depleted, why it's depleted in iron, why it has a smaller iron core basically. Whereas the dynamic simulations that actually have giant impacts specifically generate that feature. And then the final thing about the capture model is that people haven't really got their head around why the object doesn't end up colliding with the Earth eventually.
You mentioned that the moon is moving away from the Earth.
Yeah.
Is this significantly? And when do you estimate that Earth will lose its gravitational pull on the moon? What kind of effect will it have on the Earth, aside from how it will be surfing?
So it's so the answer is I don't know the exact answer to all those questions. I should get cash and memories, I'm sorry. But basically, when it first formed, the moon would have formed just beyond what we call erosion limit, and so it would have been about like 10,000 kilometers or so above the surface of the Earth. It would have occupied about a third of the night sky, and it's been gradually moving away since then. The tidal effects of having the moon so close would have been huge. So whereas we, so I was talking about it to my PA tonight actually, because she's seen that, what's that movie? Melancholy. It's a movie about another planet colliding with the Earth and the effect it has on people. And of course the movie shows these people waiting for this planet to come in and collide. Of course they're sort of lying there waiting for it to come in. And of course in reality the tidal effects would be enormous. And the surface of the Earth would be torn apart by this effect. And it's a bit the same in the early days of the Earth. You would have had this moon going around the Earth, basically totally distorting the surface of the Earth. The interior, depending on the physics of the exact interior, how solid it was, would have gone through probably dramatic melting and overturned magmatic. You've had lots of melting going on inside the deep interior of the Earth because of decompression from the interior of the Earth. So things have been highly unstable for probably for about 100 million years after the moon formed. And it's quite hard to see how you can easily get a particularly stable environment. So those models are a little bit unclear, and one of the interesting things that's come out of isotopic dating over the last decade or so has been the realization that there are grains of sand that we can date with uranium lead using the mineral zircon, which actually go back to about 4.35 billion years. These have been found in rocks in Australia in particular. Those grains of sand are basically only about 100 million years younger than the moon. So those grains of sand also have oxygen isotopic compositions that suggest there was liquid water on the surface of the Earth at the time. So there's a lot of interest in that, the idea that actually you had almost a habitable environment at a very early stage in the evolution of the Earth, only 100 million years after the start of the solar system. Again, it's 100 million years after the formation of the moon. So how quickly it really happened isn't very clear. There's one grain that they found which appears to be even older than that. There's some argument about that, but there may be evidence that there is even, if you like, regular geology going on even earlier than that. So the timescales between these early solar system processes and when we actually appear to have things happening at the surface of the Earth are getting scarily close, in terms of how little time is elapsing between the two. Doesn't quite answer what you originally quite asked me.
Okay, you said the formation of the moon happened 90 million to 150 million years after solar system. Why is there such a range of 60 million years between, obviously, knowing when
Yeah.
it was created?
It's actually 7 to about. It depends on the models. I mean, if you do the straightforward model calculation, it's about 90 plus or minus 20 million years, which I published in 2008. But it assumes certain things about the chemistry of the Earth, which people have called into question recently. And those uncertainties have the effect of making it even later. So they could extend, depending on which assumptions you make, you could extend the age to quite a bit younger. Now, of course, the obvious thing to do in terms of how young it could be, the limit is the oldest rock on the moon. Because if you've got a rock on the moon, it can't be older than the moon. So a lot of work has gone into that particular white sample I showed you, that lunar north side, 60025, in recent years. And there have been papers in Nature about that, trying to redate it to high precision. And it was seen to be very old and sort of consistent with the kinds of ages we're talking about. But those ages have been redone with more modern techniques, and they're coming out younger. And so actually, it looks like that rock may have formed 200 million years after the start of the solar system, or 100 million years after the age I've been giving you for the moon. So that's actually, if you like, we know the moon has to have formed by 200 million years after the start of the solar system in order to explain that rock. And that's about the same age as these oldest zircon grains in Australia.
Why is Mars more lucrative than Moon? I mean, in the sense that, do we think we explore Moon enough to make a statement that it cannot support life, or it is, like you said, it's geologically dead? Or is it because we know very little of Mars that we are still, we're still focusing more on it and saying that probably there's some life there could be some life on Mars, and there could be options of settling on that planet? Why is the focus
On Mars.
Yes.
So it's the fascination with Mars is partly probably to do with War of the Worlds and things, but it's mainly to do with the fact that there is evidence that there was water on the surface of Mars at one time, which appears to have disappeared. So all the more recent missions to Mars have come up with evidence of very, very good imagery. We actually know more about the surface of Mars than we know about the surface of the Earth. We've mapped it in superb detail from the satellites. It's just brilliant. So we've got fantastic information about that surface, and we can see very, very clear evidence of rivers and deltas and things like this, and processes that look like they've been formed by flowing water, and yet there's no water there now. And so the argument is that where's the water gone? Has it gone off into space? We know that there's isotopic evidence, again, that from the atmosphere of Mars, because we've measured with Viking, but also with other missions, and with Martian meteorites, that we've lost much of the atmosphere of Mars. So probably 99% of the atmosphere of Mars has been lost somehow. We don't exactly know how. So when did that loss happen? Is it possible that quite early on in the history of Mars you had more of an atmosphere, and you actually had an environment that might have been more habitable and opportunistic for life to develop? The thing that really catalyzed the focus on Mars, though, was the discovery of a meteorite back around 1995. It's published in Science magazine, which was discovered in Antarctica, which, using oxygen isotopes, they showed was a Martian meteorite. Came from the same group as the other Martian meteorites, but it was much older than anything that had been found before. And it had some features on it that looked like they were similar to the kinds of features that you see formed from microbial organisms. And so there were one or two chemical features that suggested there may have been biology going on. And this rock, Allen Hills 84001, got everybody excited, and including the US government and the president and everybody else, and they made big, bold claims about exploring Mars, rather like Kennedy had made big, bold claims about going to the moon. And so there's been a big focus in America in particular on going to Mars, and every mission that goes there has this this, the L word, basically in there, searching for life on Mars. Why it's scientifically interesting is because one of the questions we don't really understand the answer to is life easy or difficult? We don't know whether life started many times on Earth, whether we know it had a very difficult beginning. We know there's lots of bombardment and all the rest of it. So that makes you suggests that actually maybe it forms quite easily, but we don't know. And it'd be great to know that there's another place where it actually happened, and that it actually is quite plausible that life develops relatively easily. And we have no idea about that. And one of the major pushes for probably the biggest development in astrophysics these days is for searching for other planets around other stars, of which we've got several hundred, maybe over 1,000 now that we've discovered. Extrasolar planets. And again, the big push there in astrophysics has become the search for habitable environments and telltale signs of life. And huge amounts of money are going to those programs because of the possibility of finding that there is life elsewhere in the universe. And so there's a huge driver for a lot of science that goes on. And unfortunately, it's a bit too much of a driver. I think Mercury would be really interesting to work on, and Venus would be fantastic, but everybody wants to focus on it.
It's late, so best that we adjourn soon. Thank you, Professor, for the great talk. And thank you, everyone, for taking time off the very late Thursday to come here. There will be snacks outside. I hope it is served by now. So if you're keen, do stay and have a chat or something. Next week, we will be having Sir Martin Polikoff, the big hair guy, who will be talking about solvents and solutions. So if you're interested, do come along next week. And if you're not on the mailing list yet and you're interested, let me know and we can just put your name down here. Otherwise, have a good evening and have some snacks.